Good day, I'm Maile Madziva. Welcome back to our channel. Today we continue with our semester test 2 of our CIR 123, which is the second chemical engineering module at the University of Pretoria. We are looking at the 2015 version of semester test 2, and today, or in this video, we're going to be looking at part 4 of the semester test. It says that assume the ideal gas law holds true. For the production of hydrogen, a mixture of water vapor, methane, and nitrogen is charged to flow a reactor at 130 kilopascals Gauss and 400 Kelvin. Now this is the reaction equation. It goes further to say the feed gas flows into the reactor at a rate of 100 kilograms per hour. It contains the reactants in such a ratio that the excess H2O will be 30%. The feed gas also contains 8% nitrogen, which is inert. Now the question says, or the first question in A says, calculate the mole percent composition of the mixed feed gas and its flow rate in normal meter cubed per hour. Now with that said, because we are told that the flow rate is charged at 100 kilograms per hour of the feed stream, so that is actually going to be our basis. So our basis is 100 kilograms per hour of the feed stream. And if we have 100 kilograms per hour of the feed stream, then that means our nitrogen becomes 8 kilograms per hour, because we are told from the problem statement that the nitrogen is 8%. And now if the nitrogen is 8%, then that means that the remainder of the 100 kilograms per hour is 92 kilograms per hour. And this 92 kilograms per hour is water and methane. And it's important that I highlight the fact that by this time we don't really know how much of water is there and how much of methane is there, but we are certain that together water and methane combined make up 92 kilograms per hour. So now with that said, what we need to find an approach to actually solve the question or answer the question. So the easiest way is to actually work with like the moles, right? There's quite a couple of ways, but the simplest way that I found was to actually calculate, or rather deal with the moles, and that is to say, define X as the number of moles of methane in the feed gas. Why are we doing that? Remember that the methane is the limiting reactant, so the methane is going to be X, and based on it's going to be X moles, right? And based on the methane, we're going to calculate how much of water is required. And if we can find how much of water is required to react all of the methane, then we can then move further to calculate that water as in a 30% axis. So it's not really going to be difficult in that way. So we can just say let X be the number of moles of methane in the feed stream. So let X be the number of moles of methane in the feed stream. And if we have that, then we can just say that, now going back to the reaction equation, if there's X moles of methane in the feed stream, the question is how much of water is required? How much moles of water is required to react all of the methane? So with that said, we can just say H2O theoretically required is equals to also X kilomole. Right? And the reason is because, I can just write in bracket there that the ratio of H2O and methane is 1:1. So if there's X kilomole of methane in the feed stream and we know it's limiting, then the water that is required to react all of the methane also has to be X kilomole. So now already we know that the methane is X kilomole, and the water that needs to react the methane is also X kilomole. Now with that said, we can then move to deal with the fact that the water that is charged is actually not stoichiometrically correct. according to the problem statement, the water that is charged at a rate with 30% access. So we can just then calculate, now that we know how much water was required, then we can calculate how much water that was charged. So we can just say H2O in the feed stream, is equals to X kilomole, which is the theoretically required, right? Multiplied by 1.3, because it's actually in 30% access. Therefore, it's equals to 1.3x, right? So this then gives us the methane. We have the analysis or the partial analysis of the feed stream in terms of x. We know that the number of moles of the methane was x kilomole of the methane, yes, was x kilomole, and also the amount of water that was charged is then 1.3 kilomole. So with that said, then we can then move to our second step, or move to our second approach to the question, to say, if we have the number of moles, then we can actually calculate the masses of both H2O and the methane in the feed stream. And why are we then going to the masses? Remember, we have 92 kilograms per hour of the water and the methane, but we don't really know how much of water and methane is in there. And it will be very difficult to base all that on the masses. So we had to go to the moles. And then as soon as we deal with the moles using the reaction equation, then we can then go back to calculate the masses in terms of x. So now we're going to be calculating the masses in terms of x. Well, let me just say step 2. Step 2, calculate the masses of methane and H2O in terms of x. So now we're going to be calculating the masses of both methane and water in terms of x. So with that said, we can just say the mass of H2O is equals to the number of moles multiplied by the molar mass is equals to, what is the number of moles? The number of moles in terms of x is 1.3x. So we can just say 1.3x multiplied by the molar mass of water is 18. So if you use your calculator, it's going to give you 23.4x. This becomes the mass of water in the feed stream, right, in terms of x. And when we do the same with the methane, we say the mass of the methane in terms of x is equals to number of moles multiplied by molar mass is equals to x, because the number of moles of methane, we defined it as x, multiplied by the molar mass of methane is 16. So with that said, it means the mass of the methane is actually 16x. So now we have the mass of water and the mass of methane in terms of x. So we can just say, therefore, total water, total H2O and CH4 is equals to, let me not use the word total, let me just say H2O and methane in the feed stream is equals to 23.4x plus 16x, right? And if you use your calculator, that gives you 39.4x. So we have the total mass of both the combination of water and methane in terms of x. However, remember that we did calculate, because of the 100 kilomole base, we did calculate that we did find out that the water in the methane contain is actually 92 kilograms per hour. So we can simply equate the 39.4x with the 92 kilograms per hour and then solve for x. And that x then becomes, remember we defined the x as the number of moles of methane. So therefore, we can just say 39.4x, right, is equals to 92, isn't it? So therefore x is equals to 92 all over 39.4, and if you use your calculator, x gives you 2.335 kilomole, right? Remember, x, we defined it as the number of moles of methane in the feed stream. So then we know that in the feed stream, right, methane is equals to 2.335 kilomole, right? And then H2O is equals to, now let's calculate the H2O. Remember, the H2O is actually 1.3x because it's in 30% axis. So the H2O is equals to 1.3 multiplied by 2.335 kilomole, right? And if you use your calculator, the H2O, it gives you 3.0355 kilomole. So now we have the analysis of the feed stream, but we have the analysis of the feed stream. We know the water in the feed stream, even including the 30% axis. We know the methane in the feed stream, right? And we already knew the mass of the nitrogen, so we can easily calculate the mass of the nitrogen also, or rather the molar mass, the moles of the of nitrogen. So we can just say that the number of moles of nitrogen, right, in feed stream is equals to the mass of nitrogen all over the molar mass, right, and is equals to 8 kilograms all over the molar mass of nitrogen is 28 kilograms per kilomole, right? And if you use your calculator, it gives you 0.28571 kilomole. So by now we have found out how much of the water was in the feed stream, how much of the methane was in the feed stream, and also how much of the nitrogen was in the feed stream. With that said, we can actually calculate the total of the total kilomole of the feed stream, or the total moles of the feed stream. So we can just say, therefore, let me call it mixed feed stream sorry about that. Let me just say mixed feed stream, and in bracket write total, right, is equals to the number of moles of nitrogen plus the number of moles of methane plus the number of moles of H2O, right? So that is actually what it is. And then it's equals to the number of moles of nitrogen is 0.28571 kilomole plus the number of moles of the methane is 2.335 kilomole, right, plus the number of moles of water is 3.0355 kilomole, right? I hope it's visible. Yeah, it's kilomole, isn't it? And then if you use your calculator, you'll find that the total of this mixed feed stream in terms of, or rather in kilomole, is actually 5.65 621 kilomole. So this becomes the total amount of the total kilomole of the feed stream, right? And let me just bring the question just as a reminder again. They say calculate the mole percent composition of the mixed feed stream feed gas and its flow rate in normal meters cubed. So we have the total of the total kilomoles of the mixed feed stream, and we also have the individual kilomoles of each of the three compounds. So we can simply then calculate the percentage composition of each one. So we can just start with the nitrogen and say percentage nitrogen, right, in feed stream is equals to, the nitrogen we know is 0.28571 kilomole all over. The total is 5.65621 kilomole, right, multiplied by 100%, isn't it? So with that said, if you use your calculator, you'll find that the nitrogen becomes 5.051%. So this becomes the percentage of the nitrogen in the feed stream. And then we say percentage of H2O, right, in feed stream, right, is equals to the number of moles of H2O. We calculated it to be 3.0355 kilomole all over. The total is 5.65621 kilomole multiplied by 100%. And if you use your calculator, the water gives you 53.667%, right? Then we go to the methane. We say percentage of methane, right, in feed stream is equals to, the number of moles of methane is 2.335 kilomole all over the total, which is 5.65621 kilomole, right, multiplied by 100%, isn't it? So that becomes, if you use your calculator, the methanol becomes 41.282%. So now we have calculated, we managed to answer the first part of the question, where they said calculate the mole percent composition of the mixed feed gas, right? Now we need to calculate its flow rate in normal meters cubed, isn't it? So the flow rate in normal meters cubed, we can just say flow rate, right, in normal meters cubed, right? Or let me just say in normal meters cubed, and flow rate in normal meters cubed per hour, right, is equals to, when you calculate the normal meters cubed, the flow rate in normal meters cubed, you simply take the flow rate in moles or kilomoles, and you multiply it by a constant of 22.41. So our total flow rate, we know it's actually okay, here is 5.65621 kilomole. It's kilomole per hour, and everything else becomes kilomole per hour. So we can just say 5.65621 kilomole multiplied by 22.41, right? 22.41 can either have liters per mole or meter cubes per kilomole, or whatever constant there might be. But as long as we know that the constant is 22.41, we can always adjust the units depending on the flow rate we have. So it's 22.41 kilomole is 22.41 meters cubed per kilomole, right? Yeah. And here it's 5.65621 kilomole per hour. And if you use your calculator, it's going to give you 13.68 meter cubed per hour. But because it's the normal meter cubed, it's important to put the cap n here, so it becomes 13.68 normal meter cubed per hour. So this then wraps up part 4 of our semester test 2 of 2015 of our CIR 123. So thank you for your time, and I hope we meet again in our next video.